Okay. So as we said, today we're going to finish this chapter 4, and we're going to learn basically how to use one of these solvers, ODE 45, 113, 15S, or 23T, to solve a system of equations. In general, nonlinear equations. If it's a linear system, then we can get the actual exact solution. But for nonlinear system, we have to use some numerical method. And we looked for the Euler and trapezoidal method and a little bit of Runge-Kutta, just to understand that there are more than just the first order methods. And so this class we're going to learn how to use any of those ODE in MATLAB. And there are, if you want to use Python or any other software to compute the solutions, there's going to be some something similar to ODE. So the first thing that we have to take care of is this division of let's say stiff and non-stiff systems, and that is going to be a property of our multivariable function, right? So this system that we're trying to represent, trying to model, it's going to have one of those two characteristics. What do you think does stiff or non-stiff means for a system? What would be a guess?
I guess would be a stiff system or a change of input parameters doesn't respond drastically in the output of a non-stiff system with a slight change in input with a big output difference.
Okay. So it's exactly the opposite. But you're right with the idea. So not necessarily in the inputs, it can, in this case, you don't have any inputs, right? In the general case, of course, this thing is going to be a function of u too. But the idea is the same. I mean, the vector is going to be longer, the vector x. But a stiff system would be, let's say, something like this, where you have some very fast dynamics and very slow dynamics combined. Let's say a solution of a stiff system would be something like this: e to the minus 100t plus e to the minus t. Something very fast and something very slow, right? A non-stiff system is going to be either fast or slow, but it's going to have some, let's say, some non-fast behavior. That would be the general case. Of course, given a system, given some equation, we cannot know how this thing is going to behave, right? So it depends on the expertise on the system that you're dealing with that is going to tell you if your system is stiff or non-stiff. I'm going to give you a couple of examples related to the power system, but in general, it's not, there's no rule of thumb or something like it where you can classify the systems. So related to MATLAB, what do we have? So we have mainly 4 types of solvers: ODE 45, 113, 15S, and 23T. And any of those are going to be good or bad, depending on if the system is stiff or not, or the accuracy that we're trying to get for that approximation. The most common one is the ODE 45. That's the most common. So any system that you have, you can use ODE 45. It's going to be okay. It has a good low error. However, when you have some stiff system, like some approximate models of the power system, you would prefer to use 15S or 23T. So you can capture those fast dynamics. That's the idea. So I wanted to mention something. In our examples that we did with forward Euler and trapezoidal, we used some fixed H, right? Some fixed. So we have this interval from T0 to Tf, and we took a fixed H and we moved on fixed time steps. However, any of these solvers is going to take some adaptive H, depending on how fast the solution is changing. For example, if your solution is going to be something like this, probably here you need to take a lot of samples, small h's, because you want to capture that dynamic. But here, when you have some steady state, maybe you can take bigger time steps and you're avoiding taking too much of computational time. And let me tell you, that's very important, because when you're modeling a big system, things like this are gonna make a change. So if you're ODE 45 and you're modeling a system, you're using ODE 45 to solve your system and get your numerical approximation, and it's taking too long, maybe it's because you have some fast dynamics going on. So you need to change your ODE, basically. That's one of those. Or you can stay with ODE 45 and it's going to take a long time. I remember when I did my master's, I didn't know these things. And I was waiting, I would say 5 days for a simulation of 2 seconds. And then after a while, 3 years passed by, and I realized that I could have used any other ODE and it would be tremendously faster, minutes probably instead of days. So that's a big difference. That's a big difference. So as I said, for stiff systems, when we have fast and slow dynamics, we would like to use 15S or 23T. And that would be some example, kind of similar to this one, for a stiff system. And as I said, you can have an example for a linear system where you can get the eigenvalues, and so you would know how this thing is going to evolve in the phase and the complex plane. In the complex plane, you would have some modes here, right? And you would have some other modes around here. If you have that, then you have very fast dynamics here and very slow dynamics here. That's something that most of the time happens. So one of the things that you can do if you have a complete model, for example, for the power system, you can say, well, let's focus on the slow dynamics, and let's think that these dynamics are infinitely fast. And you represent those differential equations using something else, what is called a first order manifold. That's what it's called. Or you can say, let's say this thing, we're focusing on the fast dynamics. Yeah, you're gonna have multiple modes. I just representing two here. And we're gonna consider this thing is not moving, it's constant. The slow modes are so slow compared to this one that we're gonna focus on this one, and we're gonna consider this differential equations related to the slow modes to something that is constant in time. That's another approach to get a division of the fast and slow dynamics. That's certainly something that we do with power systems. So an example of a stiff system is a synchronous generator coupled with a steam turbine. So the dynamics related to the generator are going to be related to the flux linkages. You haven't studied the generator model yet, right? I think that's the next chapter. So you're going to have very fast dynamics related to the flux linkages between the windings of the generator. And those dynamics are going to be electrical dynamics. So they're going to be very fast in the order of milliseconds. However, from the mechanical side, because you're going to have some generator, coupled with some turbine, let's say steam turbine, you have some generator. So here you have some dynamics related to the flux linkages. And here you're going to have dynamics related to the mechanical torque. So these ones are very slow in the order of seconds or several seconds. And this one are in the order of tens of milliseconds. So that means that you're going to reach steady state with these ones in the order of 10, 100 milliseconds. You're going to reach steady state. But for this one, you can take 20, 30, 50 seconds to reach steady state. So this thing are going to change very fast, and then you're going to have all the other dynamics. So this is an example of a stiff system where you have fast dynamics and slow dynamics. So in power system, we do this. If you want to study what is happening in the generator, you can assume that that mechanical torque is constant. Given that this thing is constant, you analyze in a very small time scale what is going to happen with the generator when you do all the changes. However, when you want to analyze this, you can say, okay, the generator is too fast, infinitely fast. So I'm going to analyze what is going to happen in this scale together with the power system, but this thing is going to be ideal. It's going to move infinitely fast. So that's the subdivision that we have to make to use this ODE solver. So let's go to the code. What do we have? So basically, anytime that we want to solve a system of equations, x prime equals f of x, and of course, we need to know what is going to be the initial condition. This is known. Definitely known. So as you can see, we're going to use our solver. Instead of using the word solver in MATLAB, we're going to use ODE 45, 113, or 15S, or whatever. At f means that we have a function defined, a function in MATLAB, there's going to contain the differential equations here. That's what it means. So we're calling the function MATLAB f that we have defined in our code or any other file. T-span is going to be this times time interval from T0 to Tf. So we have to specify our simulation, our approximation is going to be from 0 to 30 seconds, for example. We have to say that as an input to the solver. X0 is going to be the initial value that is going to take our x. And in general, we know that that x is going to be a vector function. I mean that f is going to be a vector function, that x is going to be a vector. So we said that this is going to be x1, x2, up to xn. equals f1 of x1, x2, xn, t, up to fn, x1, x2, blah, 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 xn, t. So that's what we're meaning with this. So the initial condition, what do you think is going to be just one value, or it's going to be a vector of values? Vector of values, right? So we need to know that, and that's something that is not always known for a power system. Usually what you have to do is to solve another problem to get your initial condition. In general, you cannot say everything is zero, right? All the conditions are zero, or any number. I'm gonna try any initial condition. In general, you can't do that. You have to solve a power flow, so you get the steady state of the system, you get how the variables are in a steady state, and you use that solution of the power flow as your initial condition. That's the general procedure. Of course, you're going to study that throughout the course, but it's important to know that it's different than any other system. Generally, you can assume any initial condition, and you have your dynamics, and you see how the dynamic evolution of the variables is going to be. But here, we have to be very careful and start from the power flow solution. That's the general procedure. And options, well, I didn't ask, but have you used any of these solvers before? Or is it your first time? First time, I assume? Okay. So the last one is going to be options, some additional options. You don't have to use this part. If you want, you can specify more things, or you can leave it blank. You have to, for sure, you have to specify the function that you're using, the time span, and the initial value. Definitely those three are, you have to give that to the ODE. And options are going to be to define, for example, the relative tolerance. What is going to be the maximum error that you're going to have between your approximated solution and the exact solution? 1 times 10 to the minus 4. Or, for example, what is going to be the max time step? What is, because thing is adaptable, it's not constant. Then when you have fast dynamics, the ODE is gonna use a small time step, but you can say, okay, I don't want it to be as large as 1 times 10 to the minus 2. So you can still capture all the dynamics required. Those are the default options. And that mass matrix, mass M, that is mostly used when you have not only differential equations. Have you ever heard of differential algebraic equations? So your model is not different. It's not everything is differential equations. You have some constraints. So you have your x dot equals f of x t, bunch of differential equations, but you have some of them. They're going to be represented by this 0 equals something. So this is some not linear function, but it's something equal to 0, right? It's an algebraic equation. So in that case, you can use that mass matrix to specify there's going to be a, that's one of the ways to use this mass matrix. But so you can say this is going to be your M matrix. You're going to say this part, all these terms are going to be related to the differential equations. And this one, the rest of the other ones, and the rest is 0. So this is a diagonal matrix. The rest is going to be related to my differential equations. So implicitly, you're telling the ODE solver that you have some differential equations and the rest are going to be algebraic equations. So that's a way to do that. And I'm not sure if you're actually going to do that here in this class, but it's always good to know, because in general, models are not always just differential. You have some constraint in the way of algebraic equations, and this math matrix is one way to approach that. So that's what we have to write. When we use that, this thing internally is going to use Brown-Licata most of the time to get your solution t and x. So you're going to have a vector of time and a vector of x. So the first column is going to be, what is going to be? The solution for the first component, x1. So x1, you're going to have x1 for the time t0, it's going to be that value. For x1, for the time t1, is going to be the second value. You're going to have a bunch of values of x. So you can pair them, t and x1, and you can plot it. So t and x2, and you can plot it. You get your numerical solution. So that's pretty much it. That's pretty much it. Now we have to learn how to use it and how to code this thing in an example. So those are the two examples from the lecture notes that we're gonna solve. We're gonna build our code to get that solution. But in general, you can use with any other system. So we can look up any other nonlinear, ideally nonlinear system, and we can use this ODE to solve this function. So let's write it down. So what do we have? We have VC. That's from a previous example that you already worked on. And I think you got the exact solution at some point. It's an RC circuit, I assume so. Plus 1 over RC E. And that E of t is going to be some input, right? Given a source, I assume. Yeah. So you have a source, you have a resistor, a capacitor, and you want to know what is going to be the voltage at the capacitor. And that's your state variable. You can write that equation in terms of the integral version of this equation, and this is going to be the differential version of that same equation. So you're going to have some initial condition, V of C of T0 equals V0, which is going to be 50 volts. You're going to have some T0. 0.005 seconds. We have an input E of t, which is going to be something known, a voltage source, 50 cosine of 120 pi t. And we have the parameters. R is 500 ohms, and C is going to be 100 milli. So you have to you have your model, you have your conditions, and we have to put this in this form, right? I mean, it's already in that. Are we okay with that time? So one thing that I didn't put there, it's we're gonna get the solution up to TF 0.35 seconds. So we're simulating from 0.005 to 0.35. That's our window of time. So let's go to MATLAB. I hope now it's, yeah, much better. So this is gonna be example 4.3 from lecture notes. So we have, let's say we have our initial condition, V0, which is gonna be, we said 50 volts. We have our time span, right? Time span, which is gonna be from 0.005 to the final time, which is going to be 0.35. So that's the way to specify. Remember that at some point here, we're going to use the function that we wrote, t comma x equals the solver, which is we're going to use ODE 45. We're going to call the function, or no, we can use function. We're going to say differential equations, right? Some function. We have to use a t-span, what we called time, and we have to give it the initial condition, x0. That's what we need. So one thing that we can do here, options, and we can, let's say, you don't have to, but if you want to, max step 1 e to the -4. So that's the biggest value of that h that we're taking every step. It can be smaller than that. The ODE is gonna figure that out, but that's what we're specifying. And we're missing the ODE set. There you go. So that's basically what we have to do regarding the initial condition. So in our case, the initial condition is V0. And now we have to define our function, right? We have to define our function. So to define the function, we're going to use this command function, and the output of this function is going to be what is going to be the differential equation. Not what it has to be, our differential equation. And we're going to call this function the same name that we use here, differential equations. And what is going to be the input of this function is going to be time and our state variable, v, how did we call it? VC. Right? And we're going to write something, and we're going to end this function. So again, this function should output the differential equation, right? So we're going to have some parameters, right? R is going to be 500 ohms. C is going to be 100 to the -6. What other parameter we can use? I don't know. Omega, the electrical frequency, which is going to be 120 high. This is going to be in radians per second. What else can we use? I don't know, Vmax for the source, it's going to be 50. And I think that's pretty much it. And we have to define our E, our input, which is given by Vmax, cosine of omega t. And you can see t is going to be an input for this function. So we don't have to do anything with t in here. And then we have some output, which is going to be, what is going to be our output? it's gonna be VC over minus VC over RC plus E over RC. So we can do minus VC over R times C. So let's do it like this. Plus E, as simple as that. So that is going to be our function, right? So our output is going to be the differential equation, and everything is defined inside of the function. So that's important. We could have defined this thing in here. So what would have been the difference if we do this? It's the same? Or is any difference?
Okay, I'm not entirely sure if this is how MATLAB works, but if this file were to have another function in it, then you'd be able to use those same variables again, but like with different values if you define them inside the function.
Exactly. Yeah. So you have to be very careful. In general, when you use multiple functions, everything that you use inside of the function is better to be defined inside of that function. So that's a general rule. Couple ago was working with a very big system, and what I ended up using is just one file with all the parameters. So every time that I use a function, I would call that file and load all the parameters. It's something you can. This is a really simple example, but those small things can mess you up when you're dealing with something bigger. So in this case, if we use it here or inside the function, it's going to be exactly the same. But in general, it's better to define everything that you use here, define it here. So this should give us the solution, right? So this should give us T and X. And X in this case is just one variable. So we're going to have just one column. So let's see what we have. Oh, options. There you go. So we have some. It's not even showing. So we have X and we have T. So you can tell that this thing is not using a fixed time step, right? Because you have 13,801 points from 0.005 to 0.35 seconds. And now we can plot the solution. So we can plot T, comma, how did we call it? VC. And we have our plot. How to do it here? I mean, I used X instead of VC. So we have to use X here. That's the solution. And I think you worked out this problem on chapter 2, so you can compare the solution. I think it's kind of familiar for you. You start from an initial value of 50, and so you apply this function. So you apply this input, which is a sinusoidal input, and what this is going to happen is going to make the capacitor to this charge up to the point that it's only you're only going to have this term related to the input. And of course there is a voltage drop in the resistance, so you're gonna the voltage from the source is going to be split between the resistor and the capacitor, and this what you get at steady state here is going to be the voltage of the capacitor after a while. But you can tell that this thing is charged and it's gonna discharge up to the point that it's only gonna have the AC component. So, and we know that because we know where this equation comes from. But is it clear? Easy? Easy, right? Yeah.
So, all the functions, and you use like TVC, how does it correlate that to X?
Oh, so VC, yeah. Good question. So we could have used here VC and it's going to be the same. So the name that you put here is just the output. Always the first element is from the output of ODE is going to be the time. And all the rest variables are going to be your X's, right? So in this case, we have VC, so we can use VC is going to be the same, right?
Like, even though you called them two different things, you just associated them together.
Yeah, because you're if you put X here, you're defining the output from the ODE as X. That's the difference. Yeah. But internally, you're using the variable as VC. That's the good question. Good question. So this would be the most simple example that we can come up with. And the second one, let's work another one. We have 10 minutes. Example 4.4, which is going to be this one. So this is the same linear system that we used. Of course, we can work out any nonlinear system. But as an example, to learn how to use MATLAB, we're going to use this one. And I'm going to give you some literal homework for later. So we have x1 dot x2 dot equals some matrix A equals A. 1 minus 3 is our matrix A, x1, x2, and your initial condition is going to be 1 and 1. So this same structure that we're going to use here, you can use this for any bigger system that you want to solve for. So in this case, very easy. The differential equation is just going to be X, right? But in general, when you have multiple functions and those functions are going to be nonlinear, you have to write down every equation that you're going to have. So let's copy the same structure that we used here. So now to avoid confusion, our initial condition is going to be x0, right? And the initial condition is going to be 1 and 1. So 1, 1. And we're going to use that. So this is a column vector, right? It's a column vector. And what is the time that we're using here? It doesn't say anything. So we're going to do it. I think we used from 0 to 3 last time when we solved this. From 0 to 3. The options are going to be the same, and we're going to use, instead of this ODE 45, we're going to use 113, but it's exactly the same thing. Differential equations, time, V0 that we called X0, and our output is going to be X. And we have to come up with our function. So our function is going to be a function of X. X, we're going to call X our state variable or state variables. And in this case, we only have to define one thing, right? Which is going to be the matrix A, which is minus 1, minus 10, 1, and minus 3. there's going to be our function or matrix A, and the output, it's just going to be AX. So we have our differential equations. And now we have to select which variable we want to plot, right? So this X that is going to be the output of the ODE is going to have two main columns, one related to X1 and the other one related to X2. So we have to do some subplot, right? So let's say we have first one on the left, we're going to have all the rows and column 1, first column is going to be X1. So we're going to use some title here, and we're going to call it X1 of T. So we know which one is which. And the second one is going to be the second, all the rows, second column is going to be X2. We're going to call it figure 1. So if we run this thing, there we have our two solutions. The same one that we approximated last class, right? It's exactly the same one. So one thing that you can, well, this is a very simple system, though. It doesn't matter if you use any ODE, right? Later on in the course, you're going to look for different models of the system, their controllers and everything. And this classification, stiff and non-stiff system, is going to be very important to define which solver you're going to use. So the little homework that I want you to work on, it's, we have just 5 minutes, so there's one example pending here that we didn't work on, which is example 4.2. As you can see, this example, it's a two state variables, two equation system. So we have something like this, but now we can't express that in terms of a matrix A because it's nonlinear. So you have to get the solution for that. So that would be our little homework. Try to solve it. It's going to take 10 minutes, 15 minutes. You have to write down the code and get the numerical solution for X1 and X2. And okay, this is the pendulum with friction discussed. So you're going to have some initial condition, you're going to have some oscillations, and it's going to reach steady state at some point. So try to work out this example at home whenever you have time, and send me your results so we can discuss it. If you have any question related to the coding or anything, you can message me, you can send me an email, whatever. And one thing that you can do also is to compare the solution from the ODE and the forward Euler, backward Euler, trapezoidal. Well, in this case, it's kind of difficult. That's the point of this example, is to show that when you have this nonlinear system, it's quite difficult to solve the implicit method. Right? You have to use some Newton-Raphson. But at least you can compare the solution from the ODE. So ODE 45, let's say, versus forward Euler. That's the least thing that you can do. So that's pretty much it. What we're looking here is just the basic scheme on how to solve this. But definitely when you have 10 state variables and you have 10 differential equations that are going to be nonlinear, the structure of it is the same. Where the models are going to come from what you're going to look from the generators, the exciter, the governor equations, and everything that has to do with generators, and later on with renewables. So you have wind, solar, and those ones are going to be represented by this set of differential equations. And how do you think they're going to be combined? So you're going to have just one last thing. So you're going to have some synchronous generator, right? You're going to have some PV systems, and you're going to have some, let's say, some wind turbines. So from this one, you're going to get a set of, let's say, 12. I think it's 12 equations to represent the generator, the exciter, which is one of the controllers, and the governor, which is the turbine controller. So you're going to have 10 differential equations here. For any synchronous generator, you're going to have 10 differential equations. If you have 10 synchronous generators, you're going to have 100 differential equations. So for the PV system, which is something quite simple, you're going to have, let's say, 2 differential equations. It can be more complicated, but with 2, it's okay. And for the wind turbines, you're going to have, remember, something like 6 differential equations. So you're going to have differential equations here, differential equations here. You're going to have a bunch of differential equations, but they're going to be connected somehow, right? They're going to be connected somehow. So how do you think you're going to couple the dynamics that happen here and here and here and here all together? How do you think?
Probably with more differential equations.
That's one approach, right? So you have to model the grid. That is what is behind that. And you already kind of studied how to model the grid. The admittance matrix, the relationship between the angles and the voltages at each bus with the active power injected and reactive power injected. Do you look for the power flow formulation? So that formulation is actually something like this. Something like this. So that is going to be some bunch of set of algebraic equations. You're going to have 2 algebraic equations for every bus that you have. So you're going to have a bunch of differential equations given by the sources, some generators, turbines, battery energy storage, or whatever you have that inputs power, outputs power. And they're going to be coupled by a bunch of algebraic equations. So you're gonna end up with something like this: dynamics from the generator and the grid. And you have to solve all together. You're gonna have a lot of equations. But the only thing that you have to add here, basically, the idea is the same. You have to add the math equation. You're gonna specify. I'm gonna have 100 state equation, and I'm gonna have 200 buses, so 400 algebraic equations. And you have to define all of that. That's going to take time, but once you do it good, you have to use this exact same code to get your solution. That's how it works. That's how it works.
So for multiple equations in the code, you just put another after the comma in the function handles, you put however many function handles you have.
No, that's specified here. So this output is going to have 2 outputs, right? Because X, yeah, we define it as a 2 by 1 vector. So that's internally it knows. So one thing it's a common mistake is, for example, you start with 3 here. You specify x0 with 3 initial values, but you only have 2 here. So it's going to complain. is gonna give you some error, right? So, or what you said is true. That's it. Work out this lecture example, and if you get it right, you're kind of understanding what we're doing. That's all for today.